In this video, we're going to be looking at how to determine arc length or the length of a curve. Just like we have seen in our study of area and volume, when we find area, we are summing up rectangles to find the area of a curved region. With volume, we're summing up either cylinders or prisms to find the volume of a curved three-dimensional figure. And with arc length, we're going to use that same idea of summing up pieces to create the length of this curve. And we're going to use integrals to do that. So let's consider this curve. And let's say that I want to find the length of this curve from A to B. Now, one thing that we can do is divide up this curve into little segments, just like we would divide up a region into rectangles and add them together. I can divide this up into, I'm going to do 4 segments here. There we go. And I could, if I had, the coordinates of these points and the actual function, we could find the length of each one of these segments. We could add those lengths together. It would give us an approximation of the length of this curve between A and B. And if I use an integral and get the length of those segments to be infinitely small and sum up infinitely many of them, then we can find the actual length of this arc. So let's just focus in on one of these segments here. I'm going to look right here, and let's talk about how to find the length of it. If you remember your distance formula, it's just based on Pythagorean theorem. So I've drawn in a right triangle here where the segment that we're interested in is the hypotenuse. I'm going to label the sides of the right triangle delta y and delta x for the change in x coordinates between those 2 points and the change in y coordinates between those 2 points. And that means that the length of this segment is going to be, using Pythagorean theorem, the square root of delta x squared plus delta y squared. And so if I take infinitely many of these segments whose length is the square root of delta x squared plus delta y squared, if I do infinitely many of those, my delta x and delta y, they become dx and dy. And we could use an integral that would look like this. The integral from A to B, square root of dx squared plus dy squared. Sorry about that. And so when we look at that, seems pretty simple. But maybe you're noticing that on our integral here, there's something missing. We really need a dx out here on the end to close off our integral. And before, when we were working with area and volume, we always got that dx because it was the height of our figure. It was either the height of the rectangle or the height of the cylinder or the prism. But in this case, I'm only dealing with one dimension, and so we don't have that height that we're multiplying by. But just like we do in mathematics, when we want to change the way something looks, I'm going to multiply by 1. But I'm going to choose my 1 to be dx over dx, because that'll bring in that dx that we need at the end of the integral. Problem is I have an extra 1 down here in the denominator. And so what I'm going to do is take that dx and just move it inside the square root. We can just divide everything in the square root by the dx and kind of separate these so that I have the 1 that I need at the end of the integral. So let's see what that would look like if I rewrite the integral. A to b, square root of, so this becomes dx squared over, now when I bring the dx inside the square root, I've got to square it because it was outside the square root. If I put it inside, it needs to be squared. So I'm going to make that dx squared plus, and I'm going to do the same thing here because we need to, if we bring it in, we've got to divide everything in the integral by that dx squared. And then we still have The dx from the numerator is still on the outside. So now I'm just going to simplify this a little bit. Dx squared over dx squared, that's just 1. And then we have dy squared over dx squared, or I'm going to change that to dy dx squared. And there you have it. That is our formula for arc length. Let's look at an example. Let's say I have the curve y equals x cubed over 3, and I want to find the arc length on the interval -1 to 1. So I'm just going to use our arc length formula here. And obviously, to use this formula, I need dy dx. So I'm going to find dy dx, take a derivative of this, and we just get x squared. And now I'm going to plug everything into the formula. My arc length is going to be equal to the integral from -1 to 1 of the square root of 1 plus dy dx, which is x squared squared dx. And really, that's all there is to this. You will see with arc length that most of the time we're going to end up with something here that we cannot integrate by hand, and therefore, really our only option is to find the arc length is to put this integral into a calculator. And I have done that for us. This arc length is 2.178. And so really arc length, a very easy topic for us. The main thing is learning that formula.